Okay, welcome everyone to this continuation of what is quantum topology, already part 12, and actually the last part about categories before we go into something more exciting, namely more categories. So what is more exciting than categories? More categories, maybe. Or enriched categories, or whatever you want to call it. Okay, so today I would like to tell you about two-dimensional algebra. So here, this beautiful picture that hopefully makes some sense at this point. So with colored regions being categories, strings being functors, and little coupons type things, like this little epsilon here, for example. These are natural transformations. And I always call this a two-dimensional algebra because literally you just, fill in the plane, right? Okay, so functor calculus. Oh, you can call that functor calculus if you want. So categories, functors, natural transformations has this two-dimensional flavor using string diagrams. And kind of the important trick that you use here that you never draw identities. So if you have something like an identity functor, you never draw it. So here, let's say you have a functor from f from c to d, c to d. So C is purple, D is green from C to D, and G from D to C, so from green to purple. And let's say you have a natural transformation from FG to the identity. Then a priori you would need to draw that diagram on the right here. But it gets much nicer if you just don't draw it, and you just draw the little cup, this little cappy here. There's still a coupon. Eventually I will get rid of the coupon as well, but it's already much nicer to not draw the identities and you get this little cap. And then it's kind of fun, and I kind of feel like people knew that when they were thinking about adjoint functors. So nowadays it's clearly well known. It's kind of the motivation for adjoint functors is that adjoint functors are the correct, abstract notion to have plane geometry. So I do kind of the thing here that I'm explaining to you that adjoint functors are nothing else than plane geometry using the string diagram calculus. And again, I think this was well known from the very start, but in the early papers on category theory, it's really difficult to find any diagrammatics. So this was like not quite 100 years ago, but in the 1960s, which is not 100 years ago when I'm recording this video, but in the 1960s it literally started, and it was very difficult to have diagrams in papers. That changed a lot, by the way, if you read more modern papers. So it's kind of a little bit difficult to tell whether those people already thought in these terms or not. But anyway, nowadays I would like to do this, and here you have a little zigzag identity. So this is a very nice identity, right? And this completely makes sense in plane geometry. So it essentially ignores the coupons, and then all I have here on the left is a little string that I just pull straight back. I just pull it straight. That's it, right? Then we call it a zigzag identity. And there's another one the other way around, right? To just literally pull the string straight. And that's obviously plane geometry. Maybe not obviously. It's more like plane topology if you want. But anyway, it's like a very easy argument that everyone believes. You just pull the string straight. And there are several other compatibility conditions which also look like very nice diagrammatically. So this one is called the interchange law. Whatever, it is literally just saying if you have two natural transformations, and between f and g and between h and I, then they satisfy this sliding type rule, which from plane geometry, plane topology, makes absolute sense, right? So both of these are completely harmless looking operations that they definitely want to impose them. Yeah, zigzag, and the other one is called the interchange law. And planar diagrams, that's what you want to do with them, right? Otherwise it's boring. You want to pull strings. And we use this idea to define certain functors. This is kind of, I think, really, as I said, how adjoint functors came around, because this is literally how you would do it. So an adjoint functor, an adjoint pair, is literally an f and a g that satisfy the zigzag relation. That's it. Right? So it's kind of this plane geometry built in. So an adjoint pair is exactly that. So let's say we do that. So let's say we have functors. And again, my f goes from purple to green, and the g goes from green to purple. So you can nicely stack them together. That's the whole point, right? In both directions. And we have a cup and a cap map, and we call those natural transformations, right? So one goes from FG, from GF. Yeah? So here G, then F. I'm always reading from right to left in the function type notation. It's a bit annoying, but if you think about functions, f of x, the input is always of a function is always on the right. So this is kind of a reading convention from right to left. So first G, then F. That's a picture on the left. And at the top, I just told you we don't draw identities, so there's nothing. And similarly, we have the other way around, the map the other way around, right? And obviously, I don't really want to have those coupons, but let's keep the coupons around for now. And they should satisfy the one relation they could satisfy. In this case, there are two, actually. The two relations they could satisfy. So if you stack them together like that, in the only way that makes sense at all, you have this zigzag relation, right? You just can pull strings straight. That's it, right? And this is what I call an adjoint pair. So F and G form an adjoint pair if they have a zigzag relation. Very nice. More formally, I guess, and this is how I would like to think about adjoint functors. To adjoint functors, two functors, exactly as on the previous slide, form an adjoint pair, form an adjoint pair, if there exists a co-unit, a cup map, a unit, a cap map. So co-unit is the left guy, this is a unit, is a right guy. Satisfy the zigzag relations, and usually people write it like that, but if you just unravel that and draw the picture, this is literally just the zigzag relation. And in this case, we say F is if a left adjoint of G, and we write this F comma G type thing, and G is the right adjoint of F, and we write this, well, G on the right and F on the left. And really note that there are two types of zigzag relation, and this makes the left-right thing here. So F is the one that curls rightwards, with F on the outside here. Yeah, so G is the one that kind of curls rightwards here, so G is a right adjoint. And F is the one that curls leftwards, so F is the left adjoint. And obviously there should be a notion like something you call them bi-adjoint, if you could do it in both directions. But in this case we just have a directionness here, whether you curl it rightwards or you curl it leftwards, and one of them is then the left adjoint and the other one is the right adjoint. And yeah, so that's what adjoint functors are. They just have the zigzag relations, and this is kind of a very nice way of thinking about zigzag relations. Yeah, and they might exist or they might not exist. But if they exist, they are unique as it gets. If they exist, they're as unique as it gets, and you can literally use the zigzag relation to do whatever you want with them. So, for example, the homojunction, which is literally just saying that thing here. So you can pull F to the right, and you just need to change it to a G, yeah, and you get the same type of spaces, and you can literally see this diagrammatically. I just wrote down the maps, and if you apply the zigzag relations to them, which is kind of a nice exercise, you will actually see that these are isomorphisms. Yeah? So these are the maps realizing the isomorphism at the bottom. So adjoint functors are literally those diagrammatic tools, yeah, very nice, that just satisfy the obvious things in plane geometry. That's what adjoint functors are. Adjoint functors are topological tools. Anyway, I hope you enjoyed this video, and I also hope to see you next time.